get a different distribution of a vocabulary for different covariates, this kind of model can deliver that for you. Okay, why? Because once you have this joint distribution, you can start factoring. So you can do a lot of stuff with the joint distribution that you can't with just the conditional distribution. And that might reveal some interesting problems. So I'm not going to go through what a naive Bayes classifier is. I might leave you to work with that. It has been used, but it's a little bit outdated. Instead, I want to jump to a model that's been used more recently in the economics literature, which in a sense is more satisfying because it allows for a richer set of covariates. So basically, in a naive Bayes classifier, you would have a finite number of categories like spam email and non-spam email. And then you would infer different word distributions for spam and non-spam and use that joint model to do prediction about whether an out-of-sample document was spam or not spam. But you're restricted to predicting one of a finite number of categories, which typically isn't how we write down regression models in economics, where we have continuous covariates and then also multiple covariates, not just a single dimension of categorization. So I want to talk about this inverse regression model. So there's a kind of a nice history behind this. So an inverse regression model in statistics is a generic class of model in which I model x v given 1. Okay, that's called an inverse regression, and there's a big statistics literature on that class. Now, a well-known early example in the economics literature is an econometrica paper by Ginskow and Shapiro in 2010, where they tried to infer the slant of media outlets in the US. I briefly alluded to this, I think, in one of the opening slides. But their model was a little bit ad hoc, and that inspired their Chicago colleague, Matt Taddy, to formalize the inverse regression model for text that sort of implicitly underlies this Ginskow and Shapiro econometrica paper, which was then used again by Ginskow, Shapiro, and Taddy to measure political polarization. So there's basically a nice thread of inverse regression papers over the last decade that you can follow should you wish. Let's write it down. So for any of you who do discrete choice modeling, this is a familiar expression to you. Right? So I'm writing down, so this is the first statistical model of text that we've specified in this course. So I want to write down a data generating process for this high dimensional vector of term counts. Right? What distribution am I going to assume these term counts are drawn from? I'm going to assume they're drawn from a multinomial distribution. We briefly discussed the multinomial distribution in the pre-sessional lecture slides. So for those of you who saw it, hopefully you know what a multinomial is. It's basically tossing a v-sided coin and counting the number of times that coin shows up on each of its v sides and each flips. And that's the model that I'm writing down here. Okay, so I'm going to flip this v-sided coin in v times, and the probability that it lands on the v face is given by this expression. Okay, so QDV is the probability that term v shows up in document D. Right, so every document is going to have its own document-specific multinomial probability vector, and this is a multinomial logistic. Okay, sometimes in the machine learning literature, this is called a softmax function. So I don't study discrete choice models, but I gather that for those of you in structural I/O or other fields that do discrete choice models, this is a very common structure. Okay? So it's a linear model, a generalized linear model, in which every term has its own baseline frequency AV. There's then a set of document-specific covariates YD, whose values are allowed to influence the probability that document D has term V. All right, so BV is a set of term-specific regression coefficients. The only difference between this and standard discrete choice models is the huge number of features that can be chosen in the discrete choice model. Okay, so we're not choosing to take the train, take the bus, or take a taxi. We're choosing among these, 10,000 terms. Okay, so that makes the MLE estimates somewhat unreliable, and we need to do some regularization for estimating this model. Okay? So, there's, I guess, always a danger of putting a paper on one slide. but this TADDY paper in 2015 introduces this data generating process for text, and then makes an argument for how you contractively estimate this. So if you tried to take this and directly estimate it by MLE, it would be a hard problem, because every time you have to, deal with the denominator of these probabilities, which involves the sum over 10,000 elements. Okay, so it would be convenient to break this apart into different terms that didn't have to interact with each other in the likelihood function. So there's an argument made in this TADDY 2015 paper that you can approximate the likelihood of this model with separate Poisson regressions. All right, so if you take the R package for fitting this multinomial inverse regression model for text, what is essentially happening under the hood is assuming that each term is a Poisson given XV. Okay, so now you do capital V different independent Poisson regressions, and that's parallelizable because these things don't communicate with each other. Now that's how to approximate the MLE. We know that the MLE in this problem is going to be noisy because of the sparse counts. And so there's one more element to the model, which is to impose this lasso structure. Okay, in fact, given that we're in a probability space, a probability model, the Bayesian interpretation is explicitly made in this TADDY paper. So he calls it a Bayesian model with a Laplace prior. In fact, there's a generalization called the gamma Laplace, which allows the double exponential to have different shapes, but we don't have to get into that. In the econometrica paper, they basically take the simple lasso. So, cut a long story short, this high-dimensional discrete choice problem over vocabulary space is broken down into capital V independent Poisson regressions with a lasso penalty on the regression coefficients. And you can actually verify that writing your own R code, like building the Poisson regression models explicitly, which I could do. So it's a statistical model, not very complicated, okay, with a lot of assumed independences and pretty standard regularization. I think there was a question somewhere.
In this, in the context of regularization, would it be better here to use, for example, something like elastic net, just because we need to take into account the correlation among the words we take?
Oh, yeah, so important clarification. This Poisson, because it's an inverse regression model, we're no longer modeling the y's as a function of the x's. So these Poisson regressions actually have the x's as the outcomes, and the covariates are the.
So the lasso is on the y, not the
exactly.
Okay.
So the lasso is on these BV coefficients, essentially.
So you could use other penalization schemes.
Yeah, sure.
Reach or elastic.
Exactly. All right, so let's take this basic sort of regularized discrete choice model to a data set. All right, so this econometrica paper uses this multinomial inverse regression model to model speech data from the US congressional record. And so this is, again, a large corpus. It is freely available, all right, from 1873 to 2016. You can go download it from whatever historical archives the US government maintains. And it records every speech made on the floor of Congress in a particular congressional session, right? So in this sample period, there are 7,732 speakers. The US has a two-party system. I have to admit, I'm not sure how they deal with, so I think at certain points in this period, there were other parties, like the Whig Party or something. I'm not exactly sure how that's treated, but certainly in the last 100 years, we can think of there essentially just being two political parties. And the structure of the US Congress is such that there are two houses. So there's a Senate with 100 members, and there's a House with a varying number of members over this time period, but in the hundreds. All right, so if I aggregate all of that across the sample, I end up with this 7,700 speakers, and there are 36,000 unique speaker sessions. All right, the feature space is going to be to tabulate all unique two-word sequences, so in these bigrams, And there are 500,000 phrases that have been used at least 10 times in at least one session. So that's the capital V in this model. So I'm going to be essentially estimating 500,000 different plus operations. And you can see why parallelization is going to be important here. You wouldn't want to, deal with that dimensionality of the feature space in the raw multinomial. All right, so what controls am I going to use? Well, there's the political party. So that's the main object of interest. There's also the state that somebody comes from. So you might, if you're a Republican from Mississippi, you might be different than a Republican from Arizona. So there's this tradition of more socially conservative Republicans versus more anti-government Republicans. So geography is going to be a proxy for that. The chamber is whether you're in the House or the Senate. All right, so senators are elected for 6 years. So there's sometimes an idea that they can pander less to the public because they don't have to be reelected all the time. So maybe be a little bit more outside the political cycle and talking about more complicated intellectual things. The gender's in there, man or woman. I think there's also a set of time-fixed effects. All right, so just to convince you that political, and I was noticing as I was making slides that a lot of the examples actually do come from political economy. In a sense, the Federal Open Markets Committee could also be viewed as a kind of political economy type application, right? How do governments work? And it is true that political scientists are about 8 to 10 years ahead of the curve of economists in using these methods because text data is so central to how politics happens, right? So that's where we get party manifestos, that's where we get debates. Anyway, just to convince you that diagrams capture ideology, here's a couple of graphs from, this in fact is from the 2010 econometric paper. All right, so this is not the application of polarization, but it still gives the same idea. All right. So what's the exercise here? So they tabulate these diagrams across all speakers in the US Congress. They do a chi-square test and then rank terms according to which ones are most associated with Democrats, which is the more left-wing party, versus which one is most associated with Republicans, which is the more right-wing party. So there's an interesting kind of case study here. So at least in 2005, where this is taken, one of the phrases most often used by Democrats is war in Iraq. All right, so yeah, you go.
Why the chi-square?
Well, it's just a measure of whether or not the frequency of a particular
Is related with
feature
the
is
other.
related to one of the
Okay.
variables versus another.
Just to clarify it.
So this was during the US invasion of Iraq, and apparently Republicans, political consultants told them, whenever you speak, use the phrase war on terror. And Democrats, political consultants told them to call it the war in Iraq. All right, so there's some validity of these phrases just from looking at, the political context of the time. But then you can also see that, there's natural, Rosa Parks was a black lady who I think sat on the white part of the bus in Alabama at some point in the 1960s and became a civil rights hero. And to the extent that more left-wing politicians engage in civil rights, it sort of makes sense that is there. Right, so when you go to the phrases that are most associated with Republicans, you see this war on terror. There's other kind of nice examples. There's something called an estate tax, which is basically a wealth tax when you die. Republicans call this a death tax to emphasize the fact that the government is somehow taxing your death. All right, so keep taxes low on the wealth. Of course, emphasis on embryos and abortion and all the things that Republicans think about. Right. All right. The interesting part is once you estimate this generative model, you can start to build interesting objects, right? Because you have a probability model, you can start using the structure of that probability model in interesting ways. Right. So this is the main point of this 2019 economy paper. How can I measure polarization from political speech? And they actually sell this as a more general method for measuring the degree of segregation from high frequency count data. So apparently there's a problem in urban economics about how segregated are neighborhoods. All right, so is it the case that the rich and the poor live together, blacks and whites live together? And a similar problem shows up there, that each observation can be characterized by many separate covariates. And if you want to measure how close people are you need to think carefully about how you would regularize the system to not get these noisy estimates. So they sell it as a sort of a general tool for measuring segregation in high dimensional spaces. The particular application here is the segregation between Democrats and Republicans. All right, so let's say that I want to start doing a Bayesian update with my statistical model on the probability that somebody belongs to one political party versus another, given one randomly drawn word. Okay, so I pick one of you from the crowd, you speak one word, and I need to do a Bayesian update on whether you're a Democrat or a Republican. Well, given the estimated statistical model, I can compute Bayes' rule. So I'm assuming a uniform prior here. So your prior distribution on somebody being a Democrat or a Republican is 50-50. So that's why there's no prior distribution in this formula. And then what's left is the likelihood of being a Republican or a Democrat given the word that you spoke. So conditional on your non-party covariates, so that's my notation that packs in everything except your political party. So this would be your gender, the chamber you speak in, the state that you're from. What's the posterior distribution you would attach to somebody being a Democrat in time t, given a single word? Right? Well, I see that your word is V, right? There's 500,000 bigrams. You speak one of the bigrams. I'm then going to go to the estimated statistical model, which tells me what's the probability that a Democrat speaks term V at time t, and that's something that's there. It's got estimated in the Poisson model. So that's the probability that a Democrat speaks term V at time t, conditional on their covariance. And then I would normalize the posterior by the sum of the Democrat and the Republican probabilities. Okay. Now that's just the posterior distribution of being a Democrat conditional on one randomly chosen word. All right, to get a total measure of polarization, you can compute the expected posterior across all possible words that you might have drawn. Okay, so there's some probability distribution over the terms you would actually see in a randomly drawn person's speech. And that's what this formula is. Okay, so the expected posterior after hearing a single phrase is what? Well, there's a 1/2 chance you're a Democrat. All right, given that you're a Democrat, there's a certain probability that I would have observed you speak any particular term V. And then conditional on speaking that term V, I'm going to go to that posterior to update my beliefs. Okay, so that's basically an inner product that just goes and multiplies Q and rows together across all 500,000 terms. All right, whether there's another probability you're a Republican, there's a probability if you're a Republican you would have generated term V, and then there's a 1 minus the posterior is the probability to be a Republican. All right, so that is the generic expected posterior for being in one of the two political parties. And then in session T, I'm just going to compute the average of that value across all the speakers that I observed. So what's the intuition here? Well, let's imagine that there's perfect segregation. All right, so Republicans are the only ones that use war on terror. The posterior belief you would attach to your being a Republican after seeing war on terror would be 1. Oh, sorry, that would be 0. So there's a 0 chance that you're a Democrat. Right? And so when you get to the war on terror term in this computation, none of the weight would be in this part of the expected posterior. All of the weight would be on that part, and the thing would have moved a lot. Okay? And then I would do that term after term after term after term. If we had pure randomness, this thing would tend to be 50-50. All right, so I can basically see how this thing varies over time, and that's going to be my measure of partisanship. So the reason I'm going through this is because it shows you what the value of specifying a statistical model is and estimating it, because if I had a random forest, I wouldn't be able to do this. Right? The way I'm able to do this is because I have a statistical structure of language which lets me compute these interesting statistical objects. So there's a few graphs in the paper.
Yeah, sorry, it's just I understand that it's kind of like measuring a distance between the vocabulary. Like I'm updating, and it's how easy it is for me to identify where this person is in which group. But at the end of the day, the paper was about polarization. So I was wondering if, like in the paper, the authors explained, or in the literature of political science, people do some similar techniques, and they explain why there's a reason to say, yeah, indeed, having different vocabularies it is indeed a very good metric to understand polarization. Because I see it, but it's kind of like, can I talk about polarization or should I be more careful?
So I guess there are two questions. One is, if I want to measure polarization, should I be using speech data? The second question is, what method should I be using to measure polarization conditional on a data set? They spend a long time talking about the second problem. So there's a big literature trying to measure polarization from text, and it has varying results. And they argue it has varying results because of the failure to regularize the high dimensional space. So a lot of people use the MLE estimates of how far you and I are from each other within a statistical model, not taking into account that we're not going to overlap very much just on average, because it's hard to generate dense counts from limited data. I think there are arguments for, so there's a quotation that I took out. The argument for using speech as a measure of polarization, I think the most powerful evidence for it that I recall in the paper is public statements by political consultants, in which they are explicit about the idea that when they wanted to, so in particular, when the Republicans wanted to differentiate themselves from the Democrats, and I can go to the, oh no, I took that slide out. So in the polarization, according to this metric, you can see was fairly stable for the first 100 years of the sample, and then kind of blows up in the last part of the sample. Right? So the idea, the main finding is that polarization has risen a lot in the last decades. By the way, this is kind of a placebo test to make sure you're not artificially inducing polarization, which you might happen in the MLE estimate, where they basically randomly assign people's party labels using the sample frequency of period by period. And so the method that they are proposing does not induce polarization in this placebo test, right? The expected posterior kind of stays on. Now, when they come to explain why there was this growth in polarization, they quote some political consultants who in 1994 advised the Republican Party, which had taken a strategy to try to differentiate itself into a more radical space. And a lot of that was designing language that was provocative and inflammatory and whatnot. I mean, it's a bit anecdotal, and I'm not a political scientist, so I'm not sure. I mean, some of this is performative, right? Does it actually translate into policy differences? I'm not sure. But at least from the voters' perspective, I think even the performance in the theater of using these language seems to matter, at least according to political consultants. Yeah.
Just a question on the interpretation of the scale here. And you said before that there's a blow up of the partisanship, but I see that increasing from 50 to 51.
Yeah, so this is after seeing just one word.
Ah, it's after one word.
Yeah, so there's another graph in the paper that's quite nice, which is if I just tracked people over, so so this is the number of words. And this is the expected posterior, which we're calling, pi t or something. There's there's some relationship that looks like this. And then I think in the, post 1970, and this is 1860 to 1950. It's quite dramatic, and I think that might get to, 80% after 100 words, something like that, which is still a pretty short speech. So most of us would not observe a single word, right? We'd listen to somebody's entire speech and they'd guess where it came from. So we would need to get out in the 100 words. But I think the counterpoint maybe to your comment, Roberto, is I believe in the Civil War times, talk about polarization. Following the Civil War, they had these big debates about reintegrating the South, or whether to let Southern planters kind of re-exploit the former slaves or whatnot. My understanding is that this was pretty intense, pretty partisan. That's not showing up in language, so we can argue. Was this just theater that didn't translate into policy or not? I don't know. But the speech-based measure seems to be have very different properties in the last 30 years to before. All right, so in conclusion, document term matrix has been used to solve 4 problems. Okay, like how distant are documents from each other? Detecting concepts in documents, detecting how concepts are related, and embedding in a regression framework to try to understand how the text varies with covariance. All of those problems can be readdressed with different models, different representations of text, and we'll see that as we go over the next 3 days. This was just kind of a teaser, okay? Even within a simple text representation, you can squeeze a lot out, squeeze a lot of interesting economics out, right? But let me, oh, I pushed escape. I don't know if I'm gonna have to. Did anyone pay attention to what it actually works? So in the GitHub, I don't know if I mentioned this, but I pushed this second set of lecture slides. I will update these tonight. They're not in their final version, but I'll begin talking about this second set of lecture slides. You can see it's so preliminary, it doesn't have a title. It will be called topic models or factor models or something like that. I know it was dangerous to try to move this, so I'm just going to read it.
Yeah, if you click on more, you can hide the
And then there
bar.
was a drop down menu.
Hide from that.
All right, so I'm not gonna, so in this class of models, we're not going to incorporate sequential information. All right, so we're gonna stay with this document term matrix representation of text, but we do want to correct one of the problems of this particular representation of text. So let's, sorry. Just click what?
Clicking, yeah.
Ah. And I claim to be good with technology. All right, so here's a couple of documents in a document matrix. School, university, college, teacher, professor. School, university, college, teacher, professor. So capital B equals 5, and I have these term counts, 5, 5, 2 in document 1, 10, 4 in document 2. What is the cosine similarity / Pearson correlation between these two documents? It would be 0. Okay. What should it be? It should probably be something other than 0, because essentially it looks like thematically similar content. So sometimes in NLP, this problem is called synonymy. The idea that a single theme or a single idea can be represented by multiple individual terms. And that's a problem for the bag of words models that we just looked at. Because part of the measured heterogeneity between two documents might be heterogeneity that arises from idiosyncratic word choices that don't actually reflect different content from a thematic perspective, right? So to the extent that that's going to generate noise in any of the measures that we just looked at, that's something we might want to solve. So basically the class of model that I'm about to discuss tries to solve that problem.
This is a question. So when you were showing those democratic words in the previous one, they had Republican senators and Senate Republicans. So in that econometric paper, they would treat these two bigrams as independent
Right.
words, right?
Yeah.
Which makes no sense in them.
Right? Each one gets its own plus on all. I mean, in a sense, I don't know. So presumably the Poisson regressions for those two distinct words probably will look the same, right? I mean, to the extent that, I don't know if that's just pure randomness that's orthogonal to the structural relationship between the covariates and the words, the estimated regression coefficients might look the same. But at the very least, there'll be an addition of noise to the model that you could try to correct by modeling the cross-equation relationship that determines these should be correlated. Okay? So essentially, I guess if you wanted to stay within this world, you could start incorporating some correlation in the regression coefficients via the prior. And that's sort of what this class along is going to do. By the way, there's another problem now that we're here in natural language called polysemy, which is the same word can have multiple meanings. All right, so tank, seal, frog, animal, navy, and more. tank, seal, frog, animal, navy, war, to, document 1, document 2. The cosine similarity between these two documents is going to be high, at least relatively high, and it arguably shouldn't be, okay? Because a tank has two meanings. A tank is a place where animals live, amphibians and fish, right? But it's also part of mechanized infantry in the army. Okay, so what would you need to do to solve this measurement problem? You would need to account for the context of these two documents, and you would need to condition on the fact that you saw the words war and navy and other military things here in order to put tank into a different kind of part of the vector space than it's being put there. The models we're going to discuss in this slide deck are not solving this problem. Sequence embedding models solve this problem because they explicitly account for local context in their representations of documents. But let's get there, as our lectures progress, and just stay to solve this problem now. All right, so there's a little bit of cross-field jargon that one has to get their heads around. If I were to tell you, I've given you a set of observations with a high-dimensional feature space with a strong dependency structure, and you're an econometrician, in particular, say a time series econometrician, what's the first thing that you would do to try to control for that? You'd say, well, I'm going to do some, factor analysis / principal components analysis. Okay, so I'm gonna resolve this issue by thinking of there being a low-dimensional set of factors, right? And then each feature is going to have some loading onto those factors, and every document is going to be represented as its projection onto those factors. I'm happy to review principal components on the chalkboard if you want, but I was happy to take it as assumed knowledge for now that we can, compute the variance covariance matrix and do an eigen decomposition of it. All right, now there's something in natural language processing called latent semantic analysis. And there's this GeoWester paper, which is exactly principal components analysis. It's a small technical, issue. So they apply a singular value decomposition to X, which is not exactly the same thing as PCA because you would need to demean the matrix column-wise. But if you demeaned the matrix column-wise, the singular value decomposition would be exactly principal components analysis. Okay? So there are, there is this idea. It's in econometrics. It was in NLP. There's also some papers that apply it. And those papers have been published well, so I can refer you to this. This is a QJE paper from 4 or 5 years ago that takes the abstracts of scientific papers produced in different countries in the first part of the 20th century and compares the distance between scientific output in different countries that shifted from having good diplomatic relationships to being at war. All right, so they use World War I as a kind of a break point in the relationship between German and Austrian scientists and American scientists. And they use the distance between the scientific outputs of those countries as measured by journal articles using LSA. Okay, so they compute the documenteur matrix, do principal components analysis, project every document onto the first K factors, and then use the cosine similarity between any two documents in that projected space as their measure of document distance. Okay, so you again see, at least in my opinion, the utility of continuing to revisit the same empirical problems. Again, we see a research design based on document similarity. It's just now we have a different method of computing document similarity. We're not using TF-IDF, cosine similarity, and a raw bag of word space. We're reducing dimensionality using this LSA. All right, I don't know how much of a purist all of you are, but I kind of like to think about these dimensionality reduction techniques as standing in for a statistical model that I could estimate in principle. There is a paper, I don't know how, how well known it is. They're probably econometrics papers too. I'm referring to one in particular, machine learning, that shows that the output of principal components analysis can be rationalized as the MLE estimates of a particular kind of factor model, but that factor model is a Gaussian factor model for continuous data. you basically have a particular structure of the variance covariance matrix on the multivariate Gaussian. Is XD a multivariate Gaussian? I figured it as a draw from a multivariate Gaussian. Well, not really. Okay, it's not continuous. Okay, there's no negative values, positive values. They don't vary the reals, and it's also sparse. Okay, so whatever statistical foundations exist for principal components analysis don't really apply to this particular data structure. Okay, so you can't make some hand-wavy argument that, yeah, when I do a latent semantic analysis, I'm really just doing NLE as a particular, like the limit case of a probability model. You really need to start over and think, all right, if I wanted to write down a statistical model of where these counts came from in a way that rationalizes their correlation structure, what am I going to do? Now, some of you may, you may not care, but let me maybe tell you a few advantages, at least that I find of writing down a statistical model. Well, you may just want to understand the foundations for how the dimensionality reduction got done. Okay, it's more transparent, it's more clear. Maybe more importantly, it allows for well-defined inference procedures. So if you want to start testing the significance of the heterogeneity in a collection of documents, you sort of need a statistical model to be able to do that. Okay, our only hope of doing inference would be to build a statistical model. It turns out to be easier to interpret the content of the factors. So a model of language expressed with these multinomial probabilities is easier to imagine, all right, than how multivariate Gaussian draws are happening, at least in my mind. And it's relatively straightforward to extend and incorporate additional dependencies of interest. One thing we have not talked about yet, but what is going to come up in these slides is every row of the document term matrix is basically considered to be independent in these dimensionality reduction techniques. And the same is true of principal components. But of course, there's going to be some Stephen-specific way of speaking, right? And some Roberto-specific way of speaking. And I might want to incorporate speaker fixed effects into my data generating process to account for that. I need a statistical model to be able to do that. So let's start. Let's build a statistical model of text that incorporates this problem of synonymy. So the most famous model in this space is called latent hearsay application. And it begins with the idea of topics, which you can think of as factors. Now, in the pre-sessional materials, let me over here. We talked about a document being generated by a multinomial distribution with some probability vector beta. And then, we took as many draws as we had terms. Right? And then beta V was the probability term V appears in document D. A topic model extends this idea by having k different probability distributions. All right, so I'm not going to have a beta 1 through beta k. So now I'm going to have a topic-specific probability that terms appear conditional on that topic. Right, so that's beta kv is the probability that term v appears in topic k. So if you want to think about this in terms of a factor model, these are factors. Right, if you want to think about it in terms of a language model, these are topics. So each one of these beta distributions is meant to capture the probability distribution over words that would be induced by talking about a particular subject, essentially. So I'm no longer going to model documents in terms of word counts. I'm going to model documents in terms of how much they're discussing different underlying, topics or subjects. And then conditional on talking about a subject, that's going to induce some probability distribution over words. Okay? But there's nothing in here. There's no D written on this slide. Okay, so there's no document-specific factors. There's just a common set of factors, and the documents are going to be built up from this common set.
Yeah. Before, when we explained the bag of word model, the key assumptions was the independence of the occurrence of certain unique terms. Now that we have done the principal component analysis, can we still assume that those principal components are still IAD? Are we transforming a dependent structure into an IAD by doing this dimensionality reduction, or what's the trick?
So let me think about this in terms of like unconditional and conditional probability statements. So conditional on talking about a specific topic K, term counts are going to be, I mean, every term in a document is going to be generated independently. Unconditionally, I guess terms and documents are not going to be correlated with each other. Right? I see. All right, so let's fix ideas here. Let's say that I have, oh, and before you ask, K is part of model selection. Where does the capital K come from? Well, this is a question that's more generically true of unsupervised learning models, like what's the dimensionality of the latent space? There's a few methods that are chosen. There's a few methods that are chosen in econometrics for factor models. I'll come back to maybe the choice of K in language models tomorrow. Let's just treat it as a fixed constant now. Okay? So in this slide, K equals 2. So there's 2 of these latent factors. Each one induces its own probability distribution over a 4-dimensional vocabulary. Let's say V equals 4. And the 4 terms of wage, price, employee, and increase, and the inflation topic and the labor topic are going to induce different multinomial distributions over those 4 terms. So let's say beta 1 is the inflation distribution over terms, and coming back to this independence assumption, conditional on talking about the inflation topic, you keep drawing these balls IID. So what's the probability? And then I guess we need to define some index into 1, 2, 3, 4, okay, to specify the probabilities. So let's say wage occupies the first place, price occupies the second place, employee occupies the third place, and increase occupies the last place. So what's the probability of drawing wage conditional on talking about topic 1? That's 1/6. Okay, so there's 6 balls and one of them is wage. What's the probability of drawing the price ball? It's 1/3. Probability of drawing the employment ball is again 1/6. And then the probability of drawing the increase ball is 1/3. Okay, so that's what I mean by a factor. It's a multinomial distribution over the vocabulary space. The second topic, this labor topic, I think it's just going to have the complementary probabilities across the balls. All right, so it's 1/3, 1/6, 1/3, 1/6. There are 2 different distributions that represent 2 different topics. Now, importantly, the same term can show up in both topics, right? So if you're talking about inflation, you're generally talking about price increases, but you could also be talking about cost push inflation, which is linked to labor markets and wages. If you're talking about labor markets, you're mainly talking about unemployment and wages, but if you want to talk about real wages, you need to talk about inflation. So this is not a hard clustering model where every term is forced into one of the buckets. It has this factor structure that allows arbitrary loadings onto the vocabulary space that can be positive in all terms. Now I want to think about representing documents in this topical space. Okay, so this is a data generating process for the nth word in document D. Okay, and we're still ignoring in, so in doesn't really matter here. All right, so it's really, any given word in a document is going to have the same data generating process, whether it's the first, second, third, fourth, whatever. Right. So every document is going to have a probability vector associated to it, and this is going to live in the k-dimensional simplex. So beta D. is going to be a k-dimensional probability vector. So remember from the pre-sessional materials, k-dimensional probability vectors have to live in the k-1 simplex. And we're going to do the following. So it's the sort of hierarchical model. So there's going to be, some probability that a document's content is generated from the second topic, some probability that it's generated from the first topic. And so the first level of randomization is which bucket do I go in? And then conditional on being in a bucket, I go to the beta that's associated with that bucket and I draw my word. Okay, so document heterogeneity is encoded with this theta d, which you can think of as topic shares. So the amount of time, I might spend 50% of my time talking about inflation, 50% labor, 70% of my time on inflation, and 25% on labor. And there we go. So there's a conditional on talking about a topic, I have the same distribution, and the document heterogeneity is just the probability falling into one bucket. So those would be factor loads. We want to talk about the factor structure. Right, so here is a formal notation for this model. But I'm still modeling documents as coming from multinomial distributions. But the way I form the document-specific multinomial is via taking a document-specific weighting. And so there's going to be these set of kind of convex weights at the document level. And I'm going to combine these k different multinomial distributions over the vocabulary to have my document-specific probability vector from which my high-dimensional term counts were drawn. Okay, so it's basically wanting to estimate these thetas is the goal here, because these thetas are going to be what I use for heterogeneity now. So the role of the XDs in this model is only to inform estimation of the thetas. We're not going to use the XDs anymore to measure document heterogeneity. We're going to use these estimated thetas. All right, so what was the, I know I only have 5 more minutes, but there's a slide at least. In the pre-sessional material, if I started with this very simple multinomial model, where I had these ND draws from beta, what was the likelihood function for that? So if XD is drawn from a multinomial beta ND, the likelihood was the product over all the vocabulary terms, the probability that that vocabulary term showed up in a document, exponentiated to the number of times that vocabulary term showed up in the document. If you understood the pre-sessional material likelihood function, I'm just recopying. So how would I rederive the likelihood function for this factor model? Well, the only thing I need to do is recognize that I have a more complicated document-specific probability of term B showing up. Right? So I no longer have a single beta distribution. If I had a single beta distribution, I would just say, what's the probability V showed up? Now the probability V shows up is this, weighted average of the factors. Okay? I'm going to take the product over the vocabulary and then the product over the documents. Okay, so that's my likelihood function for this particular model. All right, so there's a nice interpretation of how you would solve this maximum likelihood problem. This model, by the way, is called probabilistic latent semantic analysis. And I think it was developed by Hoffman in the late 1990s. Well, about 10 years later, there's this machine learning paper that shows that there's a very nice interpretation about how you would view this in the maximum likelihood context. So you basically can think of it as there being two matrices. So one of it is a matrix we'll call theta, which is capital D by K, and it's row stochastic. All right, so that means every row is a multinomial probability vector. Then there's a B matrix, which is a K by V row stochastic matrix. All right, so these are the, putting each of the K topics, one per row. And then I have the sample frequency of the share of terms realized in my data set. Okay, so this X prime is the original document term matrix where you scaled every row by the document. So when you scale every row by the document length, you basically turn raw term counts into shares, right? So of the total vocabulary in row, D, what's the share devoted to term 1, 2, 3, 4, 5, 6? So the MLE of this model is equivalent to finding a matrix factorization that rationalizes the observed frequencies of the terms in this proportion space. So I guess we can, well, I guess I should stop. Maybe after an hour, it's not the time to expand these matrix implications. By the way, I don't know if I'm now going too fast. Now, obviously, this is a little bit more involved than counting dictionary terms, but we're all right. Okay. So sorry, that's a bit of a random place to stop, but whatever.